Hello, this lesson is to go over what we would have done in class on Monday the 17th. I'm sorry to leave you guys early today. I'm not feeling well at all. I'll go through what I went through with the second hour class, give you some hints on 3.2 and 3.8. Please do have them out so that we can go through these. We'll go through 3.8 first and then 3.2, and I hope you recall that 3.8 was due Wednesday. It is also on the Edmodo site. You can double check on that. 3.2 will be due tomorrow, and once we get through a couple of these examples, you'll see just how easy it is. 3.2 you got a long time ago. There are extra copies if you need them. So first off, let's look at 3.8. 3.8 looks like this. First things first, question number 3 is actually really tough because it involves putting the force at an angle. And what I'm going to have you all do is please, if you choose to do this question, this is extra credit. And if you want to figure out how to do the question, I would ask you to find an AP student, find an AP Physics student, and ask them to help you with the problem. Have them write their name down so I know who to give credit to, and you will both receive credit for getting it right for you and working on a very challenging question, and for them helping out, which is good for them because it helps them learn the concepts by teaching it. So I think you all deserve credit for that if you get that problem right. You are not going to be tested on your unit exam on this, but it is something that goes above and beyond the Call of Duty, so I figure it is worth some bonus credit. We're going to look at number 7. Number 7 is going to relate to the lab we did last week, and it tends to be a tough question, so I won't go through this with you. You might need more room than is just simply on your paper. I will try to simulate doing this with as little space as possible, but I will have to erase stuff, and it may take up a little more room than you have. So first off, what we're looking for is the coefficient of static and kinetic friction. So mu s and mu k, and we know that this is for a block with a mass of 3.25 kilograms. We're given a graph of how much force is needed to move an object. So first and foremost, you look at this graph and you see that there's a brief peak and then it kind of levels out for a while. What that tells me is that at first it took more force to move this object, so there's a brief moment where it was harder to move and then it gets easier to move. And we can remember from last week that this force that it takes at the top here must be the static friction. You must have to apply a force that's greater than static friction in order to get it to move. In this level region here, that must be related to the force of kinetic friction. So once it's in motion, it's easier to move, and whatever force we're applying must be enough to break and stay going with kinetic friction. So using those ideas, we have a couple equations that are going to go along with this. So we are going to use the friction equations. Force of friction, static friction that is mu s times n, and the force of kinetic friction is mu k times normal force. So the exact same equation except one for kinetic and one for static. So now what we have to do, in order to solve for mu s and mu k in these equations, we have to know the force and we have to know the normal force, the force of friction, and the normal force. So let's first off see, well, what would the force of static friction be here? And what I'm doing is I'm looking at this point on the graph and then saying, well, where am I at on this force? This would be 11, this would be 12, and that's like, I'm going to call that 12.8. You might think it's 12.8 or 12.9, but either one is good. I'm going to say that my force of static friction is 12.8. And if that's the case, I now know one of the values in my formula. So I can almost solve for the equation that we have on the upper right here. So what I'll do next is I'll say, hold up, I don't know the normal force. So let's solve for that. Well, there's really no solving to do. What you have to do is you have to think about the free body diagram. So this is a diagram of the block being pulled across the tabletop like we did in our lab. We know we're pulling with some force, which we're reading from the y-axis, and then there's some force of friction resisting our motion. We also know that since it's on a planet, there must be gravity pulling downwards, and since it's on a solid tabletop, there must be a normal force heading upwards. And this allows us to solve the problem. Sorry. The force of gravity must be equal and opposite to the normal force if this object is staying on the tabletop, and we know it is, because otherwise in the problem I'd have to say it's crashing through the table. So it's not really doing that. It's on the table and we're moving it. So the normal force has to be equal and opposite to gravity. To calculate the force of gravity, and therefore the normal force, we take mass times gravity, the acceleration of gravity. Since we know that the mass of this object is 3.25, we'll take 3.25 multiplied by the force of gravity. Sorry, I think I just said force of gravity. It's 3.25 being the mass times the acceleration of gravity. Very important to clarify that. I get 31.8 newtons. Now 31.8 newtons is the force of gravity, which means it has to also be the normal force. So there we go. We've already figured out the normal force. Now, our equation's complete. We know all the details. We just have to do the algebra. Doesn't look like I was able to simulate this by having the same space as y'all, but I got to write it larger so you can see it. So on your paper, maybe you can write a little smaller, or you can just add another sheet of paper onto it that you're doing the work on. So finding the force of static friction, there we are. That's our equation. We've already said that we read the force it took from the chart. It was 12.8. We don't know MUS. We know that's multiplied by the normal force. The normal force we said was 31.8 newtons. Keep in mind that last one you had to round. You had 31.85. The 5 would not round the 8 because it's an even number, just as a little side note there. Let us divide by 31.8 on this side, and both sides actually. We need to get MUS on its own. And we should find out that MUS is equal to 0.402. And again, you have an even number and there's a 5, so it won't round the even number. So our coefficient of static friction is 0.402 for this particular problem. Now, in order to solve the other part, and I'm not going to go through that with the example on here on the board with you. What I'm going to do is I'm going to give you the information and set you off on your own with that. Force of kinetic friction, we're looking at this level region here. So what you want to do is you want to say, well, where is that basically? And I'd say that's pretty darn close to being right on 11. So I'd say my force of kinetic friction is probably 11 on the dot. And then I just have to find the details of this equation. But it's really easy now because we already figured out what the normal force is. So I'll get you set up. And from here you can easily solve for what mu k is. Alrighty. From here, we're done with the sheet 3.8. This is due on Wednesday, so please keep that in mind. Let us now move on to sheet 3.2. This is what 3.2 looks like. You would have gotten this a long while ago. If you cannot find it in your folder, please, well, please get one. I guess is the best way to put it, sorry. Please ask, and then you can get a sheet. It should be on the front instructor's table. Please make sure you have this sheet out. I'm going to go over a couple of these with you, the more challenging ones, except I'm going to leave you with the most difficult because I want to leave you at least with some kind of challenge. We're going to go over letter B first because that kind of is the more difficult version of letter A, and letter A is real simple after you see how B works. And then we'll go over letter C on the front side as well. And then I'll leave the backside for y'all to work on. I'll show you one key detail with that, and then we're good to go. But first things first, let's define something. And you don't have to write this on your sheet, but please make sure you know this. Perhaps you do write it down. It's up to you. But keep in mind that magnitude means like a how much. And we're talking about vectors here. We're going back to vector math. So if you're supposed to find the magnitude of the vector, that's a how much. And in this case, we're looking at forces. So you're looking at the force. How much force is acting on the object. Direction means which way. You know you have to have an angle with that. There's going to have to be an angle, or if it's east or south or west or north or straight heading, you don't need an angle then. If it's due east, it's just east. But if it's at an angle at all, you have to include that angle theta. We're trying to find the net force, and that may sound complicated at first, but really the combination of all forces acting on an object is the net force. So when we combine and add these vectors together, your resultant, which is a term from last unit, is the net force in this excuse me, in this case. This should say then, by the way. Oh, glorious typos. And we're supposed to find the acceleration. The way you're going to do that is you recall F net equals ma. When you find the resultant of these vectors, that's going to be the net force. That must then be equal to mass times acceleration. And the mass that's given in the problem for at least A, B, and C is 5 kilograms. And by the way, something to make note of, and I'll talk about it in letter B, whichever direction the net force is going, is heading, is the exact same direction the acceleration is heading, because the net force is producing that acceleration, which means they have to be in the same direction. Let's look at question B. For question B, you have 3 vectors acting on this thing. You can do this a number of different ways. You could choose to do the XY table. It will work out just fine. I'm going to show you a brief shortcut which will help you with number 1. Whenever you add vectors, and anything we do in physics, you can separate your dimensions. X and Y's can be separated and then combine when you find the resultant. So right now I basically have a 2 going upwards and a 5 going downwards. So I'll add those two together, and what's my result of those two? Well, pretty easy. It's 3 heading downwards. So we can actually simplify this problem right off the start just by separating the two dimensions out, x and y. I can't add anything with the x portion, so it stays 4.0. I will redraw this so it's more clear to see, but I want you to see how I just combined the y's separately at first. You would have seen the same result if you did the data table. So what I end up getting is 3 downwards, 4 to the left. Okay, well, to find these now, we have to make a triangle out of this. We have to find the resultant. So I would say that I basically have this heading at an angle, and I have 3 heading downwards, 4 heading leftwards. My angle theta will be here. And like I said, the resultant will turn out to be the net force. So you already know how to do this. It's Pythagorean theorem. Your net force, in this case, your resultant, has got to be the square root of 3.0 squared plus 4.0 squared. And that's going to get you 5 on the dot. So our net force is 5 newtons. That would be the magnitude. Your magnitude. Okay. We have to find theta still. We have to find which way. We know how much. We need to know which way. So what I would suggest is that if you do the inverse tangent, you'll have your opposite, your 4, divided by your adjacent, your 3. Oops. And when you solve this, you should end up with an angle of 53 degrees. By the way, you have to be in degrees mode. I didn't say that before, but please make sure you're in degrees mode for this. We want all of our measurements in degrees, not radians. So this isn't complete yet, though, because 53 degrees can be any which way. We need to clarify which particular direction are we looking. So when you look at the triangle I've drawn, I am heading south at first, and I have to go west of south to make my angle happen. So this is 53 degrees west of south. Very important to have that note there. So the question becomes, what does our answer actually look like? Because it looks kind of like I have a lot of piecewise stuff here. Basically, our net force is equal to 5.0 newtons at 53 degrees west of south. There we go. Now, we're not quite done yet, though, because we're supposed to find the acceleration. We know that F net equals ma. So my F net, my net force, is 5.0, we found out. And that must be equal to my mass, which, if you read from the problem above, or if you read above, it says 5.0 kilograms, multiplied by A. And I'll show the work, but I think everybody's pretty clear. This is pretty basic. It's going to be 1. Take 5 divided by 5, you will get 1. So the acceleration turns out to be 1.0 meters per second squared. Is that good enough? No, it's not quite good enough. It may be 1.0 meters per second squared, but that's just a magnitude. We also need a direction. And from before, if you recall, the net force is always pointing in the same direction as the acceleration because the acceleration is caused by the net force. So it's 1.0 meters per second squared at 53 degrees west of south. There we are. That is the complete answer. Let us move on to the letter C. Letter C will give us some practice using the chart, the XY chart idea. It's the simplest way to do it. I mean, there are many ways to do these problems, but I think this is the simplest way. So I'm going to make my XY chart, and I need enough lines to cover my number of vectors. I'm going to call that vector 1, vector 2, and this one will be vector 3. So for vector 1, since it points only upwards, that means it's only y, and it's upwards, so it's positive, and then I'll fill in the value for that vector, 7 newtons. Vector 2 is pointing to the right, and it's only horizontal, so it's only x. And since to the right it's positive, so I get a positive 7.0 going to the right. And we look at vector 3, and well, it's at an angle, so it's not just x or just y. So what we're going to do with this one is we're going to break it down into its parts. But before that, let's clarify what signs it has. And since it's pointing down, it is negative for y, and left, or west, it is negative for x. So let's redraw this so we can break this down into its parts. There we are. We have a good start. We have some x portion and some y portion. And you recall from last unit doing these, I hope you recall from last unit doing these types of problems. And basically we're going to take the cosine of 45, and that's going to get us our x portion. And that is divided by the hypotenuse, that is adjacent divided by hypotenuse. And then if I was to multiply both sides by 10, sorry about the ugly work, I end up with 10 times the cosine of 45 degrees. And that's going to equal 7.07 newtons. So I can plug that in for my value on my x column, 7.07. All right, to do the y portion, or to calculate the y portion, we would take the sine of 45 degrees, and some of you out there are perhaps groaning in your minds because you realize there's a quicker way to do this, and that's just fine. There is definitely a quicker way, but we'll just be thorough for this one, and we'll talk about it in just a moment. So for this one, it's just 10 times the sine of 45 degrees is equal to y, and the answer is going to be 7.07. And the quicker way to do that, obviously, was to say it's a 45-degree triangle. The x and y portion have to be equal, so you didn't necessarily have to do that calculation. You could have just known that it had to be the same. That's fine and good. It's also good to show the work. There's nothing wrong with that. If you did not get these same results, you are in radians mode. So please, again, make sure you're in degrees mode. Those are all three of my vectors. Those are all three that are going to combine to form my resultant. And if I add these together now, my x and my y portions, if I add these together now, I can get my resultant. I get negative 0.07 and negative 0.07. Now, what we have to do is we have to redraw that triangle so we can figure out the net force acting on this object. And from there, we'll get the direction, and we'll also get the acceleration. So to draw that, I start out at some point. For the x column, it's negative, so I must draw to the left. Fill in my value so I don't need a negative sign. I've drawn to the left, it's clearly negative. And then if I draw my next vector downwards for our negative 0.7 for y, that clearly shows the direction. I don't need a negative sign on it. This will be my net force. And here's my angle. You might have noticed a coincidence in this triangle as well. Now, to find the net force, it's simply Pythagorean theorem. And you should end up with 0.10 newtons. That's our net force using the Pythagorean theorem. Next thing we have to do is figure out the angle, and there is a quick way. And perhaps you already know it, perhaps you don't. Either way, never hurts to show the work. When you do this, you should end up with 45 degrees. The reason is that the two parts of the triangle here, two legs of the triangle, those are equal, and if they are, it has to be a 45-degree triangle. Now, that's not necessarily the answer quite yet, because 45 degrees, yeah, that's theta. But again, 45 degrees could be pointing any which way 45 degrees. I want to clarify which particular way this 45 degrees is pointing. In this case, to analyze the direction for it, I would say that originally I had my vector heading west, and I had to go south from that to make my angle. So I am south of west. Excuse me. South of west. So my net force is 0.10 newtons at 45 degrees south of west. The only thing left here is to figure out the acceleration of this object. And we know that the net force is equal to ma. Net force in this case was 0.10. The mass is still 5. And then a, we must divide by 5.0 kilograms on both sides. And I believe you're going to find that this is 0.02. And technically that's not 2 sig figs, and if we're going to be consistent with our sig figs, there's our answer. And now, the other tricky thing to say here is, again, we're not done because this is only a magnitude, we need a direction, but the direction is exactly the same as before, so it's 0.020 meters per second squared at 45 degrees south of west. And that's abbreviation for south of west. All right, if you would, flip to the back side of the sheet. These problems are a little more challenging simply because they're unlabeled. That's the only thing that really makes them tricky, except for some of the later ones that get a lot more tricky. If the mass is changed to 10 kilograms, please note that. I don't say the net force with direction, but you should still find the direction. And now, the first question is giving you a hint about how to solve the second one. These two are 90 degrees apart because they're on x and y plane, separated by 90 degrees. When you look at letter B, you have 120 degrees between these two, but there's an xy plane here. Yeah, there's a separation of 90 degrees with these. There must be 90 degrees here, which leaves only 30 degrees there. So that should make that problem a little easier to do. And for letter C, if this is 30 right here, and there has to be 90 degrees in this region here, I think you can figure out what the angle is right there based upon that. So take that into consideration. Alrighty, with the time you have left today, please work on sheet 3.2, which is due tomorrow, and please work on sheet 3.8, which is due for Wednesday. Thank you for your time.